Hey guys, Aaron with Grandpa Ray's. Today we're going to do another seminar, seminar two. I don't want to scare you away, but this one is going to cover the math, chemistry, biology, and history aspects of soil. So we'll take a little deeper dive today into the structure of soil, the makeup of soil, and kind of hit on some things that are happening within the soil. So from a math perspective, a lot of what we're going to talk about is going to be based on ratios. So whether we're talking about the carbon to nitrogen ratio or the fungal biomass to bacterial biomass ratio, what we're going to see as we continue on with these seminars and dive into the soil food web or into successional growth is those ratios are really what drives the quality of the soil, the ability for that soil to grow different things, and the nutrient content of that soil. So when we think of soil and we think of math, we just need to remember ratios. Chemistry, there's always chemical processes going on within the soil. It's help weathering those particles from the parent material down to smaller particle sizes. You got chemical reactions going on between the biology in the soil, with the rainwater that's coming into the soil. That's all chemical reactions. When we think about biology, we'll really get into biology as these seminars continue. Biology is really the driving force. Biology is what Mother Nature uses to keep soil full of nutrients so that the soil can grow things. And then history. Um, we've talked in school, and we've seen things on the great empires of the world. And you think about the Aztecs and the Mayans, or maybe some Asian large empires that once were thriving beyond comprehension, and then all of a sudden disappeared. And there was everyone was questioning, well, what happened that you could have such a thriving, successful empire just disappeared? And then over the years, as they looked at this and soil scientists got involved, they actually came to the conclusion that what happened was they degraded their soils to the point that they could no longer produce food to feed the population that they had. And we're seeing something similar today, where if you look at the Green Revolution that's happened over the last 50 to 60 years, and agriculture really took that turn to we need to mass produce as much food as we can to feed the growing population of the earth, that we also went down that path of degrading our soils. Now we're still here. We did not disappear. And partly the reason that that is the case is because our knowledge of how things worked continued to grow, and we were able to cut things out of the system. We were able to develop synthetic fertilizers and herbicides and pesticides. And even though the soil conditions have been degraded again and again and again, we're still able to take a crop off of that degraded soil because our knowledge has allowed us to find these shortcuts. Now, from our perspective as food plotters, we can grow um, food plots on degraded soil. And most of us are starting with degraded soil. That is where we are. But if our goal is that we want to have the most palatable, attractive, nutrient dense food plot that we can, we really need to start taking a look at what we're doing to the soil, and then improving our soils in steps to get to the point to where we're farming our soil to create the most nutrient dense palatable product food plot that we can. And you can use this in gardening and agriculture and everything. I really believe that our agriculture system has degraded our food to something that's not what it was 60 years ago. The nutrient density of it, the actual taste of the produce is not what it was before the soils were degraded, because we're changing that system and we've turned it into more of an industrial unit in per unit out, and not focusing on the quality of the end product. So we're going to dive in a little bit farther, and we're going to talk about the soil structure, get into that and what's in the soil, and continue on through. So soil particle sizes, we talked about parent material. All soil at one time was a rock. A rock is a group of minerals that are fused together through one process or the other. So we have all the minerals and micros and macronutrients that we need in that soil. It's just that they're not in a plant available form. So as that parent material degrades, we have three soil particle sizes. We have sand, which is the largest, silt, the medium, and clay, which is the smallest. So sand, which runs from 500ths to 2 millimeters, it's a particle size. When you envision someone saying a particle, that's kind of what you'd say it looks like. It's a grain. It's a grain of sand. The good with sand is you've got a lot of large parent material that we can break down and release those nutrients either biologically or chemically to become nutrients for the plant. And we can do that a lot because the particle sizes are pretty big. The negative to sand is because they're so big, they don't pack together really well. So you end up with a situation where you've got very high permeability, which is basically just a way of saying it just doesn't hold water very well. So you get that rain, and that rain's going through there, and it is just passing through. Very low ability to retain water. The other thing, the channels are so big in sand. We talked about cation exchange capacity and the negative and positive charges. Sand has a neutral charge, so it doesn't have the ability to hold those nutrients that have been released in the soil. There's no positive or negative attraction going on. So as that water's permeating through the soil, it's also washing your nutrients down. So if you are in a very sandy soil and you're spreading granular fertilizer on it, every time it rains, you should be thankful for the rain because the rain is wetting the soil, but it's also basically taking money out of your pocket because the fertilizer that you spread is now being washed through and beyond the capability of that root to obtain. The next level is silt, and silt is the medium. We're looking at 2/1000ths to 500ths of a millimeter. Again, it's a particle. It's got that shape of a particle. Better water holding capability. It's a little bit less permeable than sand. It's smaller particle size that is either easily broken down more than sand to provide those nutrients that make them up. The issue with silt, though, is silt is very highly erodible. It doesn't stick together really well, and it has an easy process of wind erosion, water erosion, runoff. So silt is good for some things, but it's also bad because it's hard to keep it where you want it. Again, silt, we're looking at a neutral charge. It's not positively charged or negatively charged. So while there's more space because the particle sizes are smaller. There's more surface area. It can do a better job of trapping some of the nutrients in the soil and the water, but it still doesn't hold them. And then finally, we've got clay. So clay, we're looking at anything that's less than 2/1000ths of a millimeter in size. Clay is different from sand and silt as they're particles that we envision as a grain, where clay is more like a parachute. So it's flat. Because of that, as it settles a lot slower because it's got more surface area underneath that slows it down for the size of the particle itself. This also allows it to stack on top of each other very easily, which leads to very low permeability. Because of all the surface area, there's an extraordinary amount of water holding capability there. And unfortunately, that's one of the major drawbacks of clay, is that it does hold water so well. And when clay is holding water, being a parachute, what it'll do is as that water goes, it parachutes up and it swells. So now you've got a swollen soil that's inundated with water that is not allowing any air or oxygen into the soil and causing problems there. On the positive side, with clay, clay does have a charge. Clay is negatively charged. So when we talked before about humus and breaking down into fulvic and humic acids in human, one of the huge benefits of the humic acid was its negative charge. And because of that, it was able to latch on to the nutrients in the soil and not let them go out. Clay is also negatively charged, so it will also hold on to these nutrients. So the negative side is it can get way oversaturated with water. The positive side is clay holds a lot of nutrients within the soil. So looking at the soil texture pyramid, you can see that clay is on the top of the pyramid. If you have 100% clay soil, you're at the very top of that pyramid, and more than likely you're holding a lot of nutrients in there, but unfortunately, due to the large amount of water that it's also holding and the fact that it's tightly stacked together, it is still not a good environment for plants to be growing. On the left bottom, you've got sand. Again, if you're 100% sand, you're not growing much. The sand is highly permeable, and the water is just blasting through. So you cannot hold enough nutrients in the soil or enough moisture in the soil because of the permeability there. And silt, silt's kind of in that mid-range. We look at silt and we think, man, we've got it here. This is good. The problem is we can't keep it. It doesn't stick. It doesn't stay around. So when you do have the silt, while you can keep it there, it's okay. But due to the fact that it is so easily erodible, it doesn't stick around. So then with anything, you've got a combination. So if we're looking at a clay and sand mix with no silt, that gets us over here in the sandy clay. You can get down to where you have a little bit of silt involved, and then you start moving and pulling it over depending on what the percentage of clay or sandy is. If there's more clay than sand, you're looking at a clay loam. If there's more sand than clay mixed in there, you're looking at a sandy loam. The golden zone, it depends obviously on what crop you're growing and what the water and nutrient requirements are. But if you can get in this clay loam area, you're set up for a lot of success there. There are some areas that are like that, but most of us aren't. Most of us are in these outskirts. A lot of my property, it kind of hugs this line between sandy loam and loamy sand. You get down into some other areas and you might be, towards the rivers or the lakes, you're a little bit more silty clay loam. And then you can get into some southern just clay areas. So what we need to do is we need to understand what our soil is and then do the things that we can do to improve that. Now, if I've got complete clay soil, can I just bring in some silt and sand and put it on top of that? Well, if you're working with a 4-foot by 8-foot garden in your backyard and you want to grow a $10 tomato, yeah, you could probably do that. But if we're talking on an agriculture stature where we're talking hundreds of acres or even food plots as far as we're concerned, it's not going to be feasible. So what we need to do is we need to have the understanding of what our soil is, understand what our soil type, texture is going to present us for problems, and then work on the solutions with what's available to us. So we can grow really good nutrient dense palatable food plots on soil that isn't loam or clay loam if we understand up front what our challenges are and then work to alleviate them. So a lot of people have been on vacation or in the mountains or someplace and they've seen something similar to this. They see a tree growing out of a rock and you kind of pause and you look at it and you're like, how is that possible? And that just shows you that nature has a way. Nature has a way for us or for it to grow things in unusual areas if the right beneficial biology is there to allow that to happen. So what we have here is a tree that ended up growing roots in the crack of this rock that formed a symbiotic relationship with a form of bacteria called lithotropes. And the lithotropes are actually rock eaters. They are eating the rock. They're producing an exudate that is dissolving that rock. And then as they eat that rock material, they're expending waste, and that waste has become fertilizer for that tree. So it is possible to grow things in very harsh conditions if we can create that relationship. Unfortunately, what we do a lot of times is we are worsening the problem. We are causing compaction by driving over multiple times, by tilling. We are destroying the life in the soil with pesticide use and herbicide use and heavy salts that we're putting down, whether it be in fertilizers or pesticides or herbicides. And we're disrupting that natural process. And what ends up happening is we become the agriculturalist and we start worrying about yield. For us, it's we want a decent looking food plot. And then we sacrifice the palatability and the nutrition that we could be provided in that next bite. So if nature has found a way, we need to be able to work with nature to improve our soils so that we can grow nutrient dense palatable food plots that are attracting deer to our land and not our neighbors, and then are giving them all the nutrition that they need. But to do that, we got to develop that symbiotic relationship between the plants and the biology, and at the same time understand the negatives of our soil and work through that. So the big question of soil versus dirt, there's a lot of studies that have been done over the year, and Sparks did this one in 2003, where he looked at all the soils that he could around the earth and what made up what nutrients, what minerals were in that soil. And if you look at the chart there and you swing down, let's go to nitrogen, as nitrogen is something that we're all familiar with. And he's finding that the median, meaning the middle of the ground in soil of nitrogen that's in that soil, is 2,000 units. When we, think about growing corn, for example, and they say you need you want a unit of corn or a unit of nitrogen for every bushel of corn. Wow, we've got 2,000 units of nitrogen there. And then if you move over and you look at the range, even in the poorest, worst, ridiculous soils that he found, there was 200 units of nitrogen in that soil. So the nutrients, the minerals, they're there. Unfortunately, due to how we have developed our agriculture processes, our food plotting processes, what we've done is we've locked them up in the soil so the plants can't use them. We've compacted the soil. We've over salinized the soil. We've used pesticides and herbicides, and we've killed the biology in the soil. So even though these soils have these nutrients available, the plants can't use them. And if we don't have that process to have in place a system that can break down and extract these nutrients from the soil to make them plant available, we're going to be stuck in that loop of tilling and pesticides and herbicides and synthetic fertilizers. But as we'll cover over the next couple seminars, we can get out of that vicious circle and make steps towards letting nature back into the system, and looking and understanding weeds from a successional growth standpoint and nutrient availability and how it's created through biological processes and things such as the soil food web. So we'll be diving a little bit deeper into those things on the next couple seminars. But remember this slide that the stuff that you need to grow very good nutrient dense food plots is in your soil. The challenge is how do we release that? And the next presentation is a video that I like to use when I'm doing classes for the high school kids, but it's a good demonstration of dirt versus soil.
This is the Pershhouse's
All right, what I really like to point out about that video is what was the difference? What is the difference between flour and bread? And when we look at flour and how to turn it into bread, what do we need to add to it? And if you look at a bread recipe, you need to have the protein and eggs or milk. You need to have the sugar, and you need to have biology. So the yeast that's added to that system then allows everything to work together to build that structure of bread. And that's a good way to think about what we need to do with our soils. We need to take our dirt, which is the flour in this example, and we need to add these sugars and proteins, which we do that by having 365-day ground cover and roots in the ground that are producing exudates of sugars and proteins and carbohydrates through the photosynthesis process. And we need to have the biology, which is the yeast in the bread, which is our fungal, bacteria, protozoa biomass in the soil that's working that process to release things. So I hope that today you got a little bit more understanding on the structure of soil and the makeup, and a little sneak peek into what we're going to be diving into a little bit deeper next. So our next seminar, we'll talk about successional growth, and we'll talk about the soil food web and how all these ingredients work together to provide excellent soil health that is full of nutrients that allow us to then grow nutrient-dense palatable food plots that are outcompeting our neighbors and making sure that every next bite that our deer are having are as packed as nutrients as they can be. Thanks for joining today. Aaron with Grandpa Ray Outdoors.